Hello, my name is Mazen Youssef, and today I'll be presenting my project on electromagnetic levitation, maglev, and hyperloop. First, what is magnetic levitation? Magnetic levitation is a process where an object is suspended or levitated using a magnetic field. Magnetic levitation is a highly advanced technology and it has various uses across many fields. The common point in all its application is the lack of contact and thus no wear and friction. This increases efficiency, reduces maintenance costs, and increases the useful life of the system. There are two main problems to face when attempting magnetic levitation. First obstacle is to provide a strong enough lifting force to counteract gravity. The second obstacle is to ensure the stability of the system. Electromagnetic levitation is the interaction of magnetic fields produced by permanent and superconducting magnets and electromagnets in a static or dynamic mode. Similar to a magnet falling through a pipe is slowed down, anytime a conductor experiences a changing magnetic field, electric currents are induced in it to create a magnetic field to oppose that change. The interaction between the magnetic fields produces an attractive or repulsive force depending on the polarity of the magnet. The force allows for the levitation and propulsion of an object without any physical contact, and despite the advantages of requiring no energy, the application is limited due to the low lift force to magnet weight ratio. This, however, can be fixed using something called a Holbach array, which is an arrangement of the polarities of the magnets to strengthen the the magnetic fields on one side and weaken the other, that way generating more lift force. First, let us address stability. Stable levitation of one magnet by another with no energy input is prohibited by Earnshaw's theorem. Earnshaw's theorem states that a collection of point charges cannot be maintained in a stable, stationary equilibrium configuration solely by the electrostatic interaction of the charge. While Earnshaw's theorem holds true, there are ways to go around it. Earnshaw's theorem does not apply to diamagnets. These behave in the opposite manner to normal magnets owing to the relative permeability of μr being less than 1. Diamagnetic levitation can be inherently stable. The introduction of diamagnetic materials into a system at special locations can be used to stabilize the system as a whole. On smaller scales, without applying diamagnetic material, you can generate a stable levitation using the rotation of a magnet. The Holbach array is a special arrangement of the magnets by orienting the magnets so that their poles are out of phase, usually by 90 degrees. On the left here, we have a normal phase distribution, which generates a magnetic field intensity that is equal on both sides. Using a Holbach array configuration, we can generate a much stronger magnetic field on the opposing side by rerouting the magnetic field below the structure into the working surface. This is used in both particle accelerators and fridge magnets and saves on material cost. There are several applications of magnetic levitation. It's used in several aspects of the current main focus being transportation. Maglev train systems use two sets of magnets to levitate the train and propel it forwards. The lack of friction allows for a stable, high-speed travel at a very efficient energy cost. The use of electromagnetic levitation accompanied with the pressurized air and hyperloop tubes can provide an extremely fast and energy-efficient method of travel. Thank you.